Welcome back to this Introduction to Control Theory series. In the next two videos, we'll delve into the fundamental components of control systems, the plant, the controller, and the feedback loop. Over the next hour or two, we'll explore their vital roles and how they collaborate to shape the behavior of control systems. In this first part, we'll discuss the plant. In part two, we'll address the controller and the feedback loop. This is a journey through the world of control theory, where precision reigns supreme. Control theory is the silent force behind countless industries and applications, shaping the behavior of systems with exquisite accuracy. In this educational expedition, we'll explore the art and science of achieving precision in control. Imagine a chemical reactor maintaining its temperature with unwavering precision, an aircraft soaring through the skies with stability, or a robotic arm delicately assembling components. These feats are made possible by control systems that operate behind the scenes, orchestrating the symphony of machines, sensors, and algorithms. Control theory is the heart and soul of this precision. It begins with the meticulous mathematical modeling of systems, transforming real-world dynamics into elegant equations. From there, control engineers embark on a journey of analysis, designing strategies to ensure stability, transient response, and optimal performance. At the core of control theory lies feedback, the vigilant guardian of precision. Feedback continuously measures the gap between desired and actual outcomes, making minute adjustments to maintain system accuracy in the face of disturbances and uncertainties. Control engineers, the architects of precision, wield an arsenal of control algorithms, from classic PID controllers to cutting-edge model predictive controllers. These algorithms are finely tuned to balance performance, stability, and robustness, achieving precision in a diverse array of applications. But control theory isn't limited to a single industry. It transcends boundaries, playing a pivotal role in industrial automation, automotive control, aerospace, robotics, environmental control, and more. It optimizes processes, enhances safety, and transforms industries. Yet, precision in control isn't just about equations and algorithms. It's about adapting to change, embracing innovation, and considering ethical implications. Control engineers are not just stewards of precision. They're the architects of progress, ensuring that control systems evolve responsibly. In a world where precision is synonymous with efficiency, safety, and quality, the pursuit of mastering control remains ever relevant. Control theory empowers us to shape the future, harnessing the power of machines and systems to achieve our aspirations with precision. So join me on this educational voyage as we uncover the mysteries and intricacies of control theory. Together, we'll navigate the seas of precision, discovering how control systems transform possibilities into realities in an ever-evolving world. Now, let's embark on a comprehensive exploration of the plant within control systems. In control theory, the term plant refers to the physical system or process that engineers aim to manage or regulate. This component is at the very core of control systems and is responsible for producing the desired outputs or results. Understanding the plant is fundamental because it's where all the action happens. A fundamental aspect of understanding control systems is grasping the diverse characteristics that define a plant. The plant can take on various forms, each with unique traits that influence its behavior within a control system. Let's delve deeper into these characteristics to gain a more comprehensive understanding. In the realm of control systems, one of the pivotal aspects of a plant lies in its dynamics. Dynamics, in this context, refers to how a plant responds to changes in inputs over time. This characteristic serves as a crucial foundation for comprehending and effectively manipulating control systems. Plants, much like the diverse ecosystems in nature, can exhibit a wide spectrum of dynamics. Some plants showcase fast dynamics, akin to a sprinter's swift response to a starting gun. These fast-acting plants react promptly to changes in their environment or inputs. On the other end of the spectrum, some plants possess slower dynamics, resembling the delicate pace of a lumbering giant. These plants take their time to adapt to alterations in their surroundings. Understanding these dynamics is far from a mere academic exercise. It's a key to designing control strategies that can seamlessly accommodate a plant's behavior. For instance, when dealing with a plant with fast dynamics, controllers must be capable of making rapid adjustments to maintain control and stability. Conversely, plants with slower dynamics require controllers to employ strategies that anticipate changes well in advance to prevent overshooting or undershooting desired set points. The dynamics of a plant are a dynamic puzzle in themselves. They demand keen observation, mathematical modeling, and thoughtful consideration to ensure control systems operate harmoniously with the plant's inherent characteristics. As we continue this exploration of control theory, keep in mind that these dynamics serve as the foundation upon which effective control strategies are built. Within the intricate web of any control system lie two pivotal categories of variables: inputs and outputs. Understanding these variables is essential for gaining a holistic grasp of control theory, as they form the backbone of any control system's operation. Inputs, in the context of control systems, are the variables that can be controlled. These variables act as the levers, knobs, and switches that we can manipulate to influence the behavior of the system. Depending on the nature of the system, inputs can encompass an array of factors. For instance, in a climate control system, inputs might include temperature settings, pressure adjustments, and voltage levels. These inputs are the knobs that control engineers turn to achieve the desired outcome. On the flip side, outputs represent the results or measurements that we seek to control or monitor. These outputs are the indicators of the system's performance and often align with our objectives. For example, in a chemical processing plant, an output could be the temperature of a chemical reaction or the pressure within a reactor vessel. In the manufacturing setting, it might be the position of a robotic arm on an assembly line. Outputs are the gauges, sensors, and detectors that provide crucial feedback about the system's state. In the realm of control engineering, the art lies in the selection of these inputs and outputs. Control engineers carefully choose their variables to align with specific control objectives. They assess the system's intricacies, its response to inputs, and the relevance of various outputs in achieving the desired outcomes. This selection process is akin to a composer orchestrating a symphony, where each instrument, input or output, plays a unique role in harmonizing the overall performance. As we navigate further into the depths of control theory, remember that inputs and outputs form the bridge between theory and practical application. They're the variables that control engineers manipulate and monitor to fine-tune control systems and achieve precise desired results. Within the realm of control systems, a crucial characteristic that distinguishes one plant from another is whether it exhibits linear or nonlinear behavior. This distinction carries profound implications for the predictability and complexity of a control system's response. Linear systems, as their name suggests, adhere faithfully to the principles of linearity. These systems exhibit behavior that can be precisely understood and predicted through the concept of superposition. In simpler terms, if you were to double the input, a linear system would respond by doubling the output, maintaining a consistent and proportional relationship. This inherent linearity makes the responses of such systems highly predictable, akin to tracing a straight line on a graph. On the flip side, nonlinear systems defy the simplicity of linearity. They do not conform to the principles of superposition, resulting in more intricate and often unpredictable behaviors. In these systems, doubling the input might not necessarily lead to a straightforward doubling of the output. Nonlinearities introduce curves, bends, and twists into the relationship between inputs and outputs, making their behavior akin to navigating a winding road with unexpected turns. Understanding whether a plant operates in a linear or nonlinear fashion is paramount for control engineers. It profoundly influences the choice of appropriate control strategies. Linear systems lend themselves well to analytical methods, where mathematical models can precisely capture and predict their responses. In contrast, dealing with nonlinear systems often requires more advanced and adaptive control techniques, as their behavior can be complex and challenging to encapsulate within traditional models. The quest to unravel linearity and nonlinearity of a plant is akin to deciphering the unique language it speaks in the world of control theory. It guides control engineers in selecting the right tools and strategies to tame these systems and achieve the desired control objectives. As we venture further into the intricacies of control theory, keep in mind that this distinction plays a pivotal role in shaping our approach to control systems. In the intricate world of control systems, another critical characteristic that control engineers must grapple with is time variance. Time variance denotes the propensity of some plants to exhibit changing behavior over time, even in the absence of external disturbances. This characteristic introduces a dynamic dimension to control theory, demanding a more nuanced understanding and adaptive approach. In simpler terms, consider a plant as a living entity, like a tree in a forest. Just as a tree undergoes growth, changes in seasons, and adaptation to its environment, some plants within control systems can evolve in their behavior. This evolution might manifest as shifts in response times, alterations in sensitivity to inputs, or changes in internal dynamics. Understanding time variance is akin to recognizing that the control system's tree is not static, but continuously growing and adapting. Control engineers must be aware that the plant they're dealing with today might behave differently in the future. This awareness prompts the need for control strategies that can adapt and evolve alongside the changing characteristics of the plant. Designing systems capable of accommodating time variance is a complex and dynamic endeavor. It requires continuous monitoring, data collection, and analysis to detect shifts in plant behavior. Control engineers employ predictive and adaptive control strategies to anticipate and respond to these changes effectively. Think of it as a gardener tending to a garden, adjusting irrigation, pruning, and nurturing the plants to thrive in an ever-changing environment. Time variance adds an extra layer of complexity to the control engineer's toolkit. It's a reminder that control systems are not static entities, but dynamic ecosystems that evolve over time. As we journey deeper into control theory, remember that grasping the concept of time variance equips us with the insights needed to design resilient and adaptive control systems that can navigate an ever-changing landscape of plant behavior. In the realm of control systems, a formidable challenge that control engineers grapple with is the presence of uncertainty and external disturbances. These real-world adversaries can significantly impact the plant's behavior, introducing an element of unpredictability and complexity into the control equation. Uncertainty, in this context, emerges from various sources, such as variations in materials, fluctuations in environmental conditions, or inherent imprecision in sensors and measurements. It's akin to navigating through shifting sands. You can never be entirely sure of the terrain beneath your feet. Control engineers must contend with this uncertainty by devising strategies that can adapt to and mitigate its effects. External disturbances, on the other hand, are like unexpected gusts of wind or sudden changes in weather conditions. These disturbances can take various forms, including abrupt alterations in load, temperature fluctuations, or the application of external forces to the system. They disrupt the carefully orchestrated dance of control, challenging the system's ability to maintain stability and desired performance. In the face of these challenges, control systems must exhibit robustness. Robustness is the system's ability to withstand and recover from uncertainties and disturbances, much like a skilled tightrope walker regaining balance after an unexpected gust of wind. Control engineers employ various techniques, including feedback control loops, adaptive control strategies, and fault tolerance mechanisms, to enhance the system's robustness. Robust control systems are designed not only to maintain desired performance under nominal conditions, but also to gracefully handle the uncertainties and disturbances that are an inevitable part of the real-world landscape. It's akin to building a ship capable of weathering the roughest seas without losing its course. As we progress further into the depths of control theory, bear in mind that uncertainty and disturbances are the turbulent waters control engineers must navigate. Understanding how to steer through these challenges equips us with the tools to design control systems that can thrive in the face of real-world unpredictability and adversity. Within the realm of control theory, one of the defining characteristics of a plant is its level of complexity. Plants span a vast spectrum, ranging from simple single input, single output or SISO systems to highly intricate multiple input, multiple output or MIMO systems. Understanding and managing this complexity is a fundamental aspect of control engineering. At one end of the spectrum lie the simple SISO systems, which resemble straightforward puzzles with one input and one output. Controlling such systems is akin to solving basic equations with a single variable. The relationships between inputs and outputs are clear-cut and relatively easy to grasp. In contrast, at the other end of the spectrum, we encounter the complex MIMO systems, which resemble intricate mosaics composed of numerous interacting variables. These systems involve multiple inputs and multiple outputs, forming a web of interconnected relationships. Controlling such systems is akin to orchestrating a symphony with many instruments, each influencing the overall performance in a unique way. Control engineers are akin to the maestros in this orchestra, employing advanced techniques to manage and control complex systems effectively. They leverage mathematical modeling, control algorithms, and optimization strategies to untangle the web of interactions within MIMO systems. These techniques enable them to design control strategies that orchestrate the behavior of numerous variables to achieve desired outcomes. Complexity in control systems is not a hindrance, but a challenge that drives innovation. It necessitates the development of sophisticated control approaches, such as model predictive control, adaptive control, and artificial intelligence-based techniques like neural networks and fuzzy logic. These tools empower control engineers to navigate the intricate terrain of complex systems, much like skilled navigators charting a course through uncharted waters. As we journey deeper into control theory, it's essential to recognize that complexity is the hallmark of real-world control systems. Embracing this complexity and mastering the art of control within it is what distinguishes control engineers as they work towards achieving precise and desired control objectives in a wide array of applications. Understanding these characteristics is fundamental because they guide control engineers in selecting appropriate control strategies and designing systems that can navigate the nuances of different plants. As we proceed in this series, keep in mind that each plant's unique traits influence the control solutions applied to achieve precision and efficiency. Now let's dive into the critical aspect of plant modeling within control systems. Plant modeling is the process of creating mathematical representations of the plant's behavior. These models are invaluable tools that control engineers use to understand, analyze, and design control strategies. Here, we'll explore plant modeling in more depth. Within the realm of control systems, one of the foundational pillars is the process of creating mathematical representations of a plant's behavior, a practice known as plant modeling. These mathematical models serve as invaluable tools akin to blueprints that control engineers rely upon to understand, analyze, and design effective control strategies. At the heart of plant modeling lie mathematical equations, which succinctly capture how the plant responds to inputs. These equations can take on various forms, ranging from elegantly simple to highly intricate, depending on the complexity of the plant and the level of precision required. They are the language through which we converse with the plant, seeking to decipher its behavior. For control engineers, these mathematical models are akin to a treasure map. They provide insights into the inner workings of a plant, revealing how it behaves under different conditions, much like a map showing the terrain of uncharted lands. How do you have a map of uncharted lands? What a dumb metaphor. Sorry about that. By manipulating these equations and performing simulations, control engineers can explore a plant's response to a wide range of inputs, scenarios, and disturbances. The art of creating these mathematical representations is a delicate one. Control engineers must carefully select the variables to include, determine the relationships between them, and formulate equations that mirror the plant's dynamics. It's a bit like crafting a work of art, where each stroke of the mathematical brush contributes to the masterpiece of understanding. Mathematical representation through equations is the bridge between theory and application in control systems. It transforms the abstract concept of a plant into a tangible, quantifiable entity that control engineers can study, manipulate, and ultimately control. As we venture deeper into the intricacies of control theory, keep in mind that these mathematical models are the tools that guide us in our quest to master the behavior of complex systems. In the realm of control theory, transfer functions stand as a common and powerful form of plant models. These mathematical constructs serve as vital keys to understanding and manipulating a plant's behavior, particularly when examining its response in the frequency domain. Transfer functions provide a unique perspective on the plant's dynamics by relating the Laplace transforms of its output to its input. In essence, they unlock the plant's secrets in the language of frequencies. This transformation allows control engineers to gain a deeper understanding of how a control system responds to different frequencies of inputs, much like a musician exploring the harmonics of a musical instrument. The significance of transfer functions becomes evident when dealing with dynamic systems. By representing the plant's behavior in the frequency domain, control engineers can assess its stability, frequency response, and transient characteristics with precision. It's akin to studying the resonant frequencies of a musical instrument to create harmonious melodies. Transfer functions also simplify the analysis of control systems. They enable engineers to perform frequency domain analyses, such as Bode plots and Nyquist diagrams, which provide valuable insights into the system's performance and stability. These tools are like the musical score that guides a conductor in orchestrating a symphony, helping control engineers fine-tune their systems for optimal performance. Transfer functions are the lenses through which control engineers perceive and manipulate the plant's behavior in the realm of frequencies. They empower engineers to unravel the complex interplay between inputs and outputs, enabling precise control and optimization. As we delve deeper into control theory, keep in mind that transfer functions are the instruments that harmonize the dynamics of control systems, ensuring that they perform in tune with our desired objectives. In the intricate world of control systems, particularly when dealing with complex and multivariable systems, control engineers often turn to a versatile tool known as state space models. These models provide a comprehensive and dynamic representation of a system's behavior, making them invaluable for modern control techniques. At the heart of state space models lies a set of first-order differential equations. These equations serve as the language through which control engineers describe the system's dynamics. Unlike transfer functions, which focus on frequency domain representation, state space models operate in the time domain. They capture the evolution of a system's internal states over time, much like watching the intricate movements of a clock's gears. The power of state space models becomes evident when dealing with complex systems involving multiple variables and interactions. These models offer a holistic view of the system's behavior by representing it as a set of interconnected states and equations. It's akin to dissecting a complex organism to understand the functions of its individual organs and how they interact. That's kind of a gross metaphor. State space models are particularly useful for modern control techniques, such as optimal control, adaptive control, and model predictive control. They facilitate the design of control strategies that can adapt and optimize a system's performance in real time, much like a skilled pilot adjusting the flight path of an aircraft. State space models are the blueprint of control engineers, offering a comprehensive view of the system's inner workings. They enable engineers to navigate the intricate terrain of multivariable systems, designing control strategies that not only maintain stability, but also achieve precise and dynamic control objectives. As we continue our exploration of control theory, remember that state space models are the canvas upon which we paint the complex and ever-evolving dynamics of modern control systems. In the realm of control systems, one of the fundamental tenets of sound engineering practice is model validation. This critical step involves verifying and confirming the accuracy of plant models, ensuring they faithfully represent the real-world behavior of the system. Plant models, whether expressed as transfer functions or state space models, are powerful tools in the hands of control engineers. However, their true worth lies in their ability to mirror reality. Model validation serves as a litmus test to determine whether these mathematical constructs align with the actual behavior of the plant. Validation often involves a twofold process. First, control engineers design experiments or collect real-world data from the physical system. This dataset serves as the reference points, akin to the ground truth against which the model's predictions are measured. It's like taking a snapshot of the plant's behavior in the wild. Next, engineers compare the model's predictions with the observed responses from the real-world system. This comparison serves as a reality check, akin to examining whether the portrait accurately captures the essence of its subject. If the model's predictions closely match the actual plant responses, it suggests a high degree of accuracy and fidelity. Validated models are not just theoretical abstractions. They are robust and reliable tools for control system design. Engineers can trust these models to guide the development of control strategies, fine-tune parameters, and predict system behavior under different conditions. It's akin to having a reliable map that accurately represents the terrain, enabling precise navigation. Model validation is the compass that ensures control engineers stay on the right path. It confirms that the models they rely on are not mere mathematical abstractions, but faithful representations of the real-world systems they seek to control. As we venture further into control theory, keep in mind that validated models are the cornerstone of effective control system design, guiding engineers towards precise and desired outcomes. Once a plant model is established and validated, it transforms into a dynamic and potent tool for control engineers. This tool empowers them to simulate and analyze the behavior of the control system under a multitude of conditions, marking a significant leap in control system design and refinement. Simulation, in this context, is akin to creating a virtual laboratory where engineers can experiment with the control system without the need for physical prototypes. This capability is particularly valuable when dealing with complex, costly, or hazardous systems. Engineers can adjust inputs, observe responses, and assess the system's performance under various scenarios, all within the safe and controlled environment of a computer simulation. The power of simulation extends beyond convenience. It allows for a thorough and systematic testing of control strategies. Engineers can evaluate how the system behaves under normal operating conditions, extreme conditions, or in response to unexpected disturbances. It's akin to rehearsing a play under various circumstances to ensure the actors perform flawlessly, even in unscripted moments. Analysis complements simulation by providing deeper insights into the system's behavior. Engineers can scrutinize the data generated by the simulations to uncover nuances, identify bottlenecks, and fine-tune control parameters. It's akin to a detective examining evidence to solve a complex case, aiming to optimize the control system's performance. Simulation and analysis are the twin engines that drive control system design and refinement. They empower control engineers to explore, experiment, and optimize control strategies, ultimately leading to more robust and efficient systems. As we continue our journey into control theory, keep in mind that simulation and analysis are the crucibles in which control systems are forged, ensuring they meet the rigorous demands of real-world applications. In the dynamic world of control systems, there exists a powerful approach known as model-based control. This strategy directly relies on the mathematical plant models that control engineers meticulously construct and validate. Model-based control harnesses the insights embedded within these models to craft control algorithms that achieve specific performance objectives with precision. At its core, model-based control is akin to having a highly detailed map of a terrain. The mathematical models serve as this map, providing a comprehensive understanding of the plant's behavior, dynamics, and response characteristics. Control engineers leverage this map to chart a course for the control system, guiding it towards desired outcomes. The key advantage to model-based control lies in its ability to translate theoretical knowledge into practical action. Engineers design control algorithms that utilize the plant's model's insights to make informed decisions in real time. These algorithms continuously adjust control inputs based on the system's current state, desired performance, and anticipated changes, much like a skilled pilot adjusting the plane's controls to ensure a smooth flight. Model-based control is particularly valuable in applications where precision, responsiveness, and adaptability are paramount. It excels in scenarios where complex systems must meet stringent performance criteria, such as automotive control systems, aerospace applications, and industrial processes. It's akin to having an expert guide who understands the terrain intimately and can navigate through challenging conditions with ease. Model-based control is the embodiment of control theory's marriage with practical engineering. It transforms mathematical abstractions into dynamic strategies to steer control systems towards a precise and desired objectives. As we continue our exploration of control theory, remember that model-based control is the compass that leads us through the intricacies of complex systems, ensuring they operate with finesse and efficiency. In the ever-evolving landscape of control systems, advanced strategies often incorporate adaptive and learning elements. These cutting-edge systems possess the remarkable ability to continuously update their plant models based on real-time data. This adaptive capability equips them to navigate changing conditions, uncertainties, and unexpected challenges with agility and precision. Adaptation, in this context, is akin to a control system's ability to learn from experience. Just as a skilled pilot adjusts their flying techniques in response to changing weather conditions, adaptive control systems modify their strategies based on incoming data. They assess the system's behavior and performance, comparing it to their established models. If discrepancies arise, these systems recalibrate their control algorithms to better align with actual plant behavior. Learning, on the other hand, goes a step further. Learning control systems not only adapt, but also improve their models and strategies over time. They accumulate knowledge from a series of experiences, much like a seasoned chef refining a recipe through experimentation. This iterative learning process allows these systems to continuously enhance their performance, adapting not only to known changes, but also to novel situations. The significance of adaptation and learning is most pronounced in applications where control systems must contend with the dynamic and uncertain environments. Examples include autonomous vehicles, robotics, and advanced manufacturing processes. These systems thrive on their ability to evolve and optimize their performance, much like living organisms adapting to an ever-changing habitat. Adaptation and learning usher in a new era in control systems, one that mirrors the resilience and adaptability of the natural world. These systems are not bound by static models, but are dynamic entities that evolve and improve with experience. As we venture further into the frontiers of control theory, remember that adaptation and learning are the cornerstones of control systems that can thrive in the face of complexity and uncertainty. Plant modeling is the fundamental step in control system design. It enables control engineers to gain a deep understanding of how the plant behaves, predicts its responses, and develop control strategies that can achieve desired outcomes efficiently and accurately. As we continue in this series, you'll see how these models are put into action to create effective control systems across various applications. To grasp the versatility of control systems, consider these real-world examples. In the realm of chemical manufacturing, control systems play a pivotal role in ensuring product quality, safety, and efficiency. Imagine a large-scale chemical reactor used to produce pharmaceuticals or specialty chemicals. Precise temperature control within the reactor is crucial. A control system continuously monitors and adjusts the heat input to maintain the desired temperature, preventing reactions from going awry. This not only guarantees product quality, but also enhances safety by preventing overheating or temperature fluctuations that could lead to dangerous situations. In automotive manufacturing, control systems are the backbone of modern assembly lines. Robotic arms equipped with advanced control algorithms weld and assemble parts with incredible precision. These robots follow predefined trajectories and adapt to variations in part positioning. They execute tasks with speed and accuracy, ensuring the consistent quality and efficiency of the assembly process. Control systems optimize the movement of these robots, minimizing cycle times and production costs while maintaining high-quality standards. In the aerospace industry, the plant is often the entire aircraft, and the control system responsible for its stability and safety is the flight control system. This system includes various components like sensors, actuators, and control algorithms. It continuously monitors the aircraft's state and adjusts control surfaces, such as ailerons, elevators, and rudders, to ensure stable flight, responsive handling, and passenger safety. In-flight control systems are designed to operate in diverse conditions, from takeoff to landing, making real-time adjustments to maintain stability even in turbulent skies. These examples illustrate how control systems are integral to diverse industries, from manufacturing to aerospace. They highlight the critical role these systems play in maintaining quality, safety, and efficiency in complex processes and applications. As we explore the world of control theory, these real-world instances serve as a vivid reminder of how control systems are the unseen hands guiding the success of numerous industries. Controlling different types of plants can indeed present a myriad of unique challenges, each demanding a tailored approach. These challenges stem from the diverse characteristics of plants, which can vary widely in terms of their behavior, dynamics, and environmental interactions. One notable challenge arises from the presence of nonlinearity in some plants. These systems don't conform to a simple linear pattern of input and output relationships. Instead, their behavior can be complex, featuring curves, bends, and nonlinear responses. Control engineers tackling such plants must employ specialized strategies, such as nonlinear control methods or adaptive control, to effectively manage their intricate dynamics. Navigating these nonlinear landscapes is akin to mastering the art of guiding a ship through turbulent waters. Uncertainty and external disturbances are another formidable challenge in plant control. Many real-world plants are subject to uncertain factors, such as variations in materials, environmental conditions, or inherent imprecision in sensors. Additionally, external disturbances like sudden load changes, temperature fluctuations, or external forces can disrupt control systems' equilibrium. Control engineers must design systems that are robust enough to withstand these uncertainties and disturbances, much like building structures capable of withstanding unexpected seismic events. The challenges in plant control are a testament to the diversity and complexity of the systems we seek to govern. Control engineers must don multiple hats, acting as detectives to decipher nonlinear behaviors, as navigators to steer through uncertainty, and as guardians to protect against external disturbances. As we delve deeper into the intricacies of control theory, remember that these challenges are the crucibles where innovative control strategies are forged, ensuring the efficient and safe operation of diverse plant types across various industries. Control engineers occupy a central and indispensable position in the world of plant control. Their expertise and insights are the guiding force behind the optimization, safety, and efficiency of complex systems across a multitude of industries. Control engineers begin their journey by delving deep into the behavior of the plant. They act as the detectives, meticulously analyzing the plant's dynamics, responses to inputs, and sensitivity to external factors. This deep understanding forms the foundation upon which all control strategies are built. Once the intricacies of the plan are unraveled, control engineers embark on the task of constructing mathematical models. These models are more than equations. They are the essence of the plant distilled into a mathematical form. Developing these models is akin to an artist capturing the essence of a subject in a portrait, with every variable in relationship carefully crafted to mirror reality. Armed with mathematical models and a profound understanding of the plant's behavior, control engineers set out to design control strategies. These strategies are the algorithms that govern the system's responses to inputs and disturbances. Control engineers aim for precision, robustness, and efficiency in these strategies, much like a maestro composing a symphony to evoke specific emotions. The ultimate goal of control engineers is to ensure that the plant operates optimally. They navigate the plant through varying conditions, adapting and fine-tuning control strategies as needed. They are the vigilant guardians, tirelessly monitoring the system's performance to maintain desired outcomes. Control engineers are not confined to a single industry. Their skills are highly versatile, spanning applications in manufacturing, aerospace, robotics, chemical processes, and beyond. They are the bridge between theory and application, adapting control theory's principles to real-world scenarios. Control engineers are the architects and custodians of precision and efficiency in complex systems. They are the unsung heroes behind the scenes, ensuring that our industrial processes run smoothly, our transportation remains safe, and our systems respond with accuracy to our commands. As we delve further into the world of control theory, let's acknowledge the vital role control engineers play in shaping our modern world. As we progress in this series, remember that the plant is where it all begins, and it's where control systems work their magic to bring about the results we desire. Our goal is to equip you with a deeper understanding of how control engineers navigate the complexities of different plants to achieve control and precision. Thanks for tuning in. I hope you found this video informative and thought-provoking. This is the point at which others tell you, if you enjoyed it, give it a thumbs up and consider subscribing for more content just like this. But we all know that kind of thing is for losers. Don't be a loser. And as always, I welcome your feedback and ideas for future videos in the comments section below. Until next time, keep exploring, keep learning, and keep embracing your inner nude. dude.